Okay, so let's get started. So what I want to talk about is constraint dynamics. So constraint dynamics. Specifically the reduced coordinates or reduced or generalized coordinates approach. So let me start just recapping quickly the notation. So we have some state vector x, which is made out of n particles, x1 up to xn. All of these guys would be like a three-dimensional vector as usual. So this would be a 3n dimensional column vector of particle positions. The thing that we always do. These particle positions are, of course, a function of time. And by dot, I mean the time derivative. So if I write x dot, that means the first derivative in time. Then I have x double dot is the second derivative in time, aka acceleration, right? The other thing we're going to need is the mass matrix. So that's going to be 3n by 3n. And let's just say diagonal matrix, not to dramatize things too much. And we can also say that it's constant. So in this notation, I could write it as m dot equals 0, just to practice the notation slightly, okay? And then I have a vector of forces, which are also, which is also a 3n dimensional vector. It would be typically a function of x. Typically would be like a function of x, the vector of forces, and that's the forces acting on all of the particles. So far, I'm just recapping the notation of our standard setup. Okay, is everything clear? Are you guys there?
Yes, it is.
Yes. So in your previous notes, this x was a q. Is that correct?
Yes, that's possible. Now I'm going to change the notation slightly. So
oh no, that's not correct. A q was your generalized coordinates. Never mind.
Okay, well, so x is the coordinates of all the particles. So I assume I have a system of n particles. Each of them has a certain mass, which is described by the mass matrix. And the x1 is the three-dimensional coordinates of the first particle, x2 is the 3D coordinates of second particle, and so on. Okay?
Okay.
All right. So now we need to talk about D'Alembert principle. So the first thing to talk about is the virtual displacement.
Right.
So that's usually
the particle
There's a question?
Yeah, so the particle positions are all, they're all column vectors. Okay.
Yes, they are all little three-dimensional column vectors. That's right. Okay, anything else? So the virtual displacement, it's also a 3n dimensional vector, just like the positions vector. And what does it mean? It basically means an infinitesimal change of positions of all the particles. Okay. Why it's called virtual displacement? That just means that it's not the real displacement the system will take when it's moving in time. Okay. The actual displacement is this is x dot. That's the real displacement. Okay, or the real velocity if you want. But the delta x is like a hypothetical one. Okay. And the virtual displacement we need to formulate the D'Alembert's principle, which is kind of the key to constraint dynamics. So D'Alembert's principle. You can maybe switch off the microphone too, we'll get less noise there. Unless you want to ask something, of course. So, D'Alembert's principle. It says just this, that f minus m x double dots dot product with the virtual displacements equals 0 for any valid virtual displacements delta x. Okay. So this valid doesn't make sense yet, okay, because I didn't started talking about constraints. So right now, that without any constraints, actually any delta x is valid, okay? So, and because delta x is a vector from R3n, that means that absolutely any R3n vector is valid, okay? So this equation, let's see, where is my, oh, I don't have my pointer anymore, because I'll just do this. So this equation needs to be true for arbitrary vector delta x, okay? So that means it needs to be true also for standard basis vectors, right? And if we plug in standard basis vectors, well, we get nothing but f minus m x double dot equals 0, which is nothing but Newton's second law, right? F equals m x double dot. Okay, is that clear?
So wait, could you explain the part about standard basis vectors again?
About what?
So what are the standard basis vectors?
Oh, so standard basis vectors are vectors basis. So that would be like E1, which would be a vector just 1, 0,
Sure.
0, 0, 0. Okay, that would be a 3-dimensional vector. Then I have E2, that would be a second standard basis vector. It would be 0, 1, 0, and the rest are zeros. Okay, and so on. So I have 3n standard basis vectors. There's only 1, 1, zeros everywhere else, right? So and I can take the E1, okay, and I can plug it in for the delta x, okay. I can put it here. I can plug it in here for the delta x.
Okay, so if the delta x is any of the standard basis vectors,
then what do you get? You isolate that.
Then you get.
You isolate
right, then
that.
You just get Newton's second law.
Exactly. If you plug in all of them there. If you plug in E1, you isolate the first coordinate. If you plug in E2, you isolate the second coordinate, and so on. So ultimately, you isolate all of the coordinates, and you just get that the f minus mx double dot itself needs to be 0. Okay, this thing is a dot product. Okay, so it's like a sum.
Sure.
Okay. So this is just to say that if you don't have any constraints, then D'Alembert's principle is equivalent to Newton's second law. So it's kind of not interesting, right? The things we are interested in now are the constraint dynamics cases. Okay. So for example, so let's actually look at some kind of examples to give it to be a little bit more concrete. So for example, third example could be bead on wire. Okay. So let's say bead is a single, so I have some wire kind of thing, and there is a bead, which is like a single particle, which has the standard 3D coordinates, but it has to stay on the wire. Okay, it's like this toy when there's a hole in the bead, and it can move arbitrarily, but it has to stay on the wire. Okay, and the way we can reason about this mathematically is by taking the parametric expression of this curve, right? That's going to be a function from R1 to R3. That's the parametric expression of the curve. And we can write every allowed position of our bead as a function of theta. And that's exactly this, okay? It's the function that maps some parameter, which would be like the, let's say it would be the arc length of the bead. So this would be my theta from some start. And would give me the 3D coordinates for the given theta where the particle is going to be. Okay, it's exactly parametric expression of a curve. Okay. If that's clear, then I'll move on to another example. Another example is double pendulum. I think I prepared an image for this. So let me grab that. Here is a figure of how the double pendulum setup looks like. So what we have here, so we have 2 point masses. Here is 1, and here is another one. Okay, here they say that they have masses m1 and m2, so that's fine. That would be in our case in the mass matrix. And this thing is a rigid link. Here is some kind of wall or some kind of rigid support kind of thing. Here is another rigid link. Okay, so this is why it's called double pendulum. It's a pendulum with another pendulum attached to it. Okay. And to completely characterize the position of the system, we need only two parameters. The θ1, which is the angle between the vertical axis and the direction of the first part of the pendulum, or the first pendulum. And the θ2, that's again the angle, here it is angle kind of thing. The angle between the vertical axis and the second pendulum. Okay, so we have all in all two parameters, which we can then use to formulate this function x, which would be a function from R2, θ1 and θ2, to R6, where the R6 would be just the two 3D coordinates of the two particles, okay? One particle and the second particle. Each of them had 3 coordinates, so that's why here I have the R6, okay? So that's a second example, and a third and probably the most important example is a rigid body. So if I have a single rigid body, one way I can look at the rigid body, so let's say this is my rigid body, one way I can look at it that it's made out of lots of small particles, okay, like atoms or molecules or whatever you wanna, or just like some small blobs of material, that kind of doesn't matter. And there is an arbitrary number of these particles and they're all over the place, okay? But it's a rigid body, right? So I know it has only 6 degrees of freedom, 3 translational degrees of freedom and 3 rotational ones, okay? So I can completely parameterize the position of a rigid body using these 6 parameters, 3 translation parameters, 3 rotation parameters, which maps to 3n dimensional vector, where n is the number of particles I use to discretize my rigid body, okay? And the n can be arbitrary, okay? And now the question I have is, how can we write the equations of motion in these generalized coordinates, okay? In these reduced coordinates, okay? That's why I guess they are called reduced, because there is usually fewer of them than the Cartesian coordinates, okay? These guys on the output, these would be sometimes called the Cartesian coordinates because they are expressed in some Cartesian coordinate space or world space, okay? So for the rigid body, the motivation is kind of obvious, right? If you have a rigid body, you don't want to, like, say, pick n to be like 1,000,000 or whatever you think is enough for your discretization, and then be dealing with simulation of 1,000,000 particles with lots of constraints between them, which correspond to the rigid body constraints, right? A rigid body constraint just means that the distance between every pair of particles needs to be constant as the rigid body moves. Okay, so clearly simulating 1,000,000 particles would be inefficient, so that's why we are looking for formulating the dynamics directly in these reduced coordinates, directly in the 6 coordinates, okay? In which case it doesn't even matter how many particles we use to discretize the rigid body, and we can even use eventually infinitely many of them. All right, so the question is how to write the equations of motion in generalized coordinates. And the key to the answer is exactly the D'Alembert's principle, which I introduced here. Except that when we are dealing with any of these constraint cases, the trick is that these delta axes are no longer arbitrary, okay? Remember, here I said for any valid virtual displacement, okay? So when you have a constraint system, it's no longer the case that any virtual displacement would be valid, okay? That's not true, right? Because for example, here I could in the rigid body case, I could displace the particles in a way that would violate the rigid body constraint, or actually deform the body, so that would not be a valid virtual displacement, okay? So a valid virtual displacement is only a virtual displacement that's actually compatible with my constraints. The constraints are not negotiable. I cannot possibly violate them. Okay, those are super hard. They are hard constraints. Sometimes there's the concept of soft constraints, but that doesn't apply here. When I say constraints, it means that's it. The constraint needs to be satisfied, period. Okay. So we need to do some trickery here because not every delta x is allowed in the D'Alembert's principle. So what we need to figure out is what of the delta x's, what virtual displacements are actually possible given our constraints. Okay, and that's actually kind of simple, because all we need to do is to use the Jacobian of this x function. Okay, so this x function is essentially the parameterization function, or maybe you can call it, for short I call it parameterization. You can also call it the mapping from the reduced or generalized coordinates to the Cartesian coordinates. Okay, so in general this function would go from some d dimensions of the reduced coordinates to my 3n dimensions of my Cartesian coordinates. Okay, and what I can do, I can look at the Jacobian of that function x, which is going to be a 3n by d dimensional matrix, right? That's the usual Jacobian kind of deal. So in each of the rows, I have each of the components of the function. So here I have x1 and so on up to x3n, which I can also write, if you want it to be completely explicit, as a partial derivatives. This would be the first reduced coordinate up to x1. This would be the last, the dth reduced coordinate. Here would be x3n by q1, and finally x3n by qd. All right, that's just Jacobian. And by the way, for brevity, I will just denote the Jacobian of x as j. Okay, is for Jacobian. And remember that this is 3n by d dimensional matrix, which, by the way, depends on the current state q, on the current set of generalized coordinates q. Which kind of makes sense, right? If you rotate the rigid body to some other position, then the Jacobian is going to change. That's what Jacobians usually do. All right, so back to how do we parameterize the set of allowed virtual displacements? So thanks to the Jacobian, that's quite simple. The allowed virtual displacements can be written as the Jacobian times the virtual displacement in the generalized coordinates. Okay? So all this means is that I can slightly infinitesimally displace each of my reduced coordinates, and the Jacobian tells me the corresponding displacement in all of the particles. Okay, that's exactly what Jacobian is. Okay, that's kind of like a reminder of what Jacobian is. Jacobian is the linearization of some function. In this case, the function is the function mapping from the generalized coordinates to the Cartesian coordinates. My x function here. Oops, that's not what I wanted. I meant this. That's my x function. Okay, this j always denotes a Jacobian of the x function. Okay. By the way, this is true not only for the virtual displacements, this is also true for the real displacements, so for the time derivative. Okay, so the x dot equals j times q dot. Okay, and again, the Jacobian depends on q, so if I was to be precise, I would be writing j as a function of q, because at a different set of generalized coordinates, I get a different Jacobian. Okay, but usually I don't want to do so much writing, so instead of this, usually I'll just be writing j. Okay, so is that clear so far?
Yes, seems so.
Okay, great. All right.
So some authors define the Jacobian as the transpose of that, but anyway, it doesn't matter as long as you're using consistent notation.
Yeah, that's right. Sometimes the Jacobian is defined as transpose of that, yes. But let's stick with this notation. All right, so now what we are gonna do, we are gonna put this together, okay? So we have the D'Alembert's principle. So let me copy over the D'Alembert's principle. The D'Alembert's principle says that 0 is f minus mx double dot transpose delta x, okay? And now I have the parameterization of the allowed virtual displacements like this, the j delta q. So if I just plug it in here, I'll get this, okay? F minus m times acceleration dot product the Jacobian times delta q, okay? Where delta q is the virtual displacement in generalized coordinates, okay? Delta q, of course, is also a d-dimensional vector, okay? And if my generalized coordinates are good, meaning that that means that any delta q is a valid virtual displacement in the generalized coordinates. Okay, by good I mean that there is not some, there are no some bugs like some dependencies between the generalized coordinates that actually they would not be independent or something like this. So if they are fine, the generalized coordinates, then you can now apply the same reasoning as before. You can say, okay, so now every delta q is valid, okay? So I can plug in all of the d standard basis vectors of the Euclidean space R2D, okay? And what do I get? Well, I get, of course, f minus mx dot transpose j equals 0, okay? Because again, by plugging in the standard, oh, this was supposed to be oh no, the transposition is there. Then I can isolate all of the coordinates by plugging in all of the standard basis vectors, okay? just like before. The only difference is that now I get this extra j here, which is actually important, because that's essentially the way how forces from the Cartesian coordinates get converted into forces in the generalized coordinates, okay? Yeah, I'm not sure what I was gonna show here. I think I was just gonna remind you that the J is a 3n by d dimensional matrix, so the delta q is a d-dimensional thing. So again, plugging in all the standard basis vectors isolates all of the components. So you can also transpose the whole thing. So you can also write it like this as J transpose f minus m x dot equals 0. I just transposed both sides of the equations. So you can also you can just say that JTF equals JTMX double dot. Okay, so this JTF, this is what I meant by the generalized forces. Okay, this essentially is a conversion of the forces from the Cartesian space to the generalized coordinates, okay, because the JT is a d by 3n, right? Your f was a 3n by 1, so the whole thing is going to be a d by 1 generalized forces, okay? So at this point we are halfway through only, okay? Because now we have successfully reduced this to d equations. This is only d equations, which is good. But we are not quite done yet because we still have this x here, okay? And the x still has 3n coordinates, okay? So we still don't want to be solving for all the 3n coordinates. So what we would like to do next is to replace this x double dot with an expression that contains only the q, okay? So how do we do this? That's the second part of the derivation. Well, we already know that the x dot equals jq dot. Okay, that's kind of what we had here. That's simply that's basic chain rule. Okay, or intuitively what the Jacobian means. I guess maybe it's worth mentioning that the x depends on q, right? That the That's simply because the x is a function of q, and q is, by the way, a function of t, okay? This is something you always need to keep in mind. The coordinates, generalized and Cartesian, they are always a function of t, okay? And in this formulation, the x is a function of time indirectly, only through q, okay? So if you do the time derivative of this whole thing, it's just an exercise in differentiation, then that this amounts to exactly jq dot, okay? Just the chain rule. Now we have to do it again, right? Because here we have, oops, that's not what I wanted. Because here we have x double dot, okay? So we have to differentiate again. So let's do that. So if we differentiate with respect to time again, then I apply the chain rule, Okay, that's gonna be J dot Q dot plus J Q double dot. Okay. Now, what is the J dot thing? The J dot is a little bit funny. Remember again that the J is actually a function of Q, okay? And the J is a 3n by D matrix, okay? So if I'm differentiating this with respect to time, that means that I am differentiating the Jacobian itself with respect to Q, with respect to the generalized coordinates, okay? And then again, by chain rule, I'll multiply this with Q dot, okay? Because this thing, if the Jacobian is a 3n by D matrix, if I differentiate by time, time is fortunately just a scalar, okay? So this is still a 3n by D matrix. But when I differentiate the 3n by D matrix by the D generalized coordinates, this needs to give me a 3n by D tensor, okay? But the tensor immediately disappears because then I'm immediately contracting it with a d by 1 vector, okay? So all in all, I get back a 3n by D dimensional matrix, okay? Yeah. Does that make sense? Are you guys still with me?
Yes, it's fine.
Okay, great. All right, so the next thing we are going to do, we're going to combine these things. We are basically just going to plug in for the x double dot the expression we got here. Okay, so just going to put these things together. So let's do that. So let's do, so what we're going to do is JTF. I'm just copying the left-hand side. Or let me just copy that to be clean. Mx double dot, and I'll just plug in for the x double dot what I got here. So that's the J dot Q dot plus JT, the mass matrix, times JQ double dot. Okay? Hope I did it correctly. I think so. And this thing, this formula, which I denote with a star, those are equations of motion in generalized coordinates. Okay, now they are in generalized coordinates because I no longer have any x there. I have just this q, okay, and the q is a d-dimensional vector, the vector of generalized coordinates. That depends on time, of course. And I have d equations, okay, so it's all nice. Everything has been reduced. I no longer have to go to the full Cartesian space. In the case of a rigid body, I don't even have to know how many particles it has been discretized with, okay. So that's nice. This is, by the way, the Barov and Witkin style derivation of the generalized equations of motion in generalized coordinates. Usually, you see these equations written in the following form, which I'll first write in, then I'll explain it. Q and Q dot equals some G, where what this means, this NQ means exactly my JTMJ, and this C, that's called C because it represents Coriolis and centrifugal forces. That's the term JTMJ dot times Q dot. Okay, so this thing here is exactly this term, okay, and this NQ, that's this JTMJ thing, okay, without the Q dot, and this G, that's the vector of my generalized forces, so the GTF, okay, d-dimensional vector of generalized forces, which can also depend on whatever, okay. Usually it depends on Q. Sometimes, rarely, it could depend on time too, and potentially it could depend also on Q dot if you are dealing with some damping in generalized coordinates. But the basic case is where G depends on Q only. But we don't have to worry about that now. Maybe some remarks here. This NQ, actually some people write this as M, because this is essentially the generalization of the mass matrix, okay? this n of q is what the mass matrix becomes in generalized coordinates. Okay, because kind of if you stare at this long enough, you kind of see the Newton's second law in it. Okay, because clearly here you have q double dot, right? So those are accelerations. This is some kind of this nq is some sort of generalization of the mass matrix. Okay, and these guys here, those are the fictitious forces like Coriolis and centrifugal forces, which appear due to the curvature of your parametrization. Okay, I'll explain it a little bit better. So let's talk about the C term here. This one, those are the Coriolis and centrifugal forces. So those are sometimes called fictitious forces, and they are there because our parametrization, due to curvature of x, okay, of our parametrization function, okay, because notice if j was constant, okay, that means that the gradient of j would be 0, okay, which means that the j dot would be 0, which means that this whole term would be 0, okay? So if the Jacobian was not changing as you change your generalized coordinates, this term would not exist, which is what happens in the Newton's second law expressed in Cartesian coordinates, okay? But because here we are considering cases when we have generalized coordinates which contain angles, like a rigid body motion, or even the double pendulum, right, that also has 2 angles in it, that's why these Coriolis and centrifugal forces appear, okay? Or they basically follow from the differentiation. This is kind of just explaining the difference between this form, between this form and Newton's second law, okay? Just this, some quick comment on this generalized mass matrix. The interesting thing is that this generalized mass matrix actually depends on the Q, okay? And if you think about it, that also makes sense because the mass distribution depends on the state, okay? Because the whole thing moves, so the mass matrix in this case changes as the system moves. Okay. So this formula is just a trivial rewriting. It's just change of notation of this formula, the one I denoted with the star. Okay. Is this all clear?
Yes, it is.
Cool. So the last thing I would like to mention is that sometimes this is actually derived from Lagrange's equations. Okay. So there is a different derivation that actually leads to the same result. That's what I originally got wrong, but it actually does lead to the same result. So that's the last thing I would like to show you, because that's how you usually see this derived. I think this derivation is kind of clean and easy to follow. The Lagrange's one has some different advantages, okay? So let's look at the Lagrangian viewpoint. Lagrangian view. Okay, so it all starts with the kinetic energy. Okay, so we write the kinetic energy. And again, we are talking about a system with generalized coordinates. So we can write the kinetic energy as a function of the generalized coordinates, both of the generalized positions as well as of the generalized velocities. Okay, and what the kinetic energy is going to be is simply the how should I write this? Let me do this a little bit slower. So this is going to be the velocities in the Cartesian coordinates in a mass matrix norm squared. Okay, in case you haven't seen this notation before, this simply means xt transpose x dot t mx dot. Okay, so that just means take all of my coordinate velocities, square them, multiply them by their masses, sum it together, divide by 2. Okay, that's what kinetic energy is. Now I want to write it in terms of the generalized coordinates, which I can thanks to the Jacobian, right? So I can write this as jq dot, and this stays the same, okay? Which again, if you want, I can expand this to q dot transpose j transpose m j q dot, all right? So that's the expression for the kinetic energy. And then then I will need to differentiate the kinetic energy by Q and by Q dot. Okay. So just to make the notation simple, I will just say that this gradient 1 of t, that means differentiation by the first argument by Q, and the gradient 2 of t is gonna mean differentiate by the second argument, the Q dot. Okay, so the t is a function of two d-dimensional vectors, q and q dot. Where is the q here, by the way? Let me see. Where is the q there? Why do I have the q here? Just to make sure we are on the same page.
Well, q dots of...
I didn't hear that.
Never mind. You can kind of express q dot as a function of q if you consider the chain rule.
No, you cannot.
Oh.
The q
it's
dot.
the Jacobian, right?
Yes. The q dot here is not a function of q. Okay, those are like positions and velocities. They are related, but they are related indirectly. Okay, not as far as kinetic energy is concerned. So q dot is not a function of q. That's good. The q is a q and q dot. They are all functions of time. Okay, that is true. And that's kind of the ugly thing here, right? That kind of this is something you need to carry in your mind. The notation does not reflect this. You need to remember it. Which is kind of sad, but that's what it is. So someone else?
Is it the Jacobian?
Yes, exactly. The Jacobian depends on Q, okay? So again, this is something you need to carry in your mind, something you need to remember. So the Jacobian and the Jacobian transpose, of course, if I was meticulous, I would be writing all the time this, okay? But that would be a lot of writing, so I'm not writing the Q there. The Jacobian depends on Q, okay? And that's why I have the Q here. Well, that's going to be clear when we write the Lagrange's equation, okay? So Lagrange equation says that the time derivative of the gradient 2 of t minus the first gradient of t equals the generalized forces, okay? So this g is the same as this g, which is the same as JTF, okay? So what we're going to do is we're going to look at this left-hand side of Lagrange's equation. Sometimes this is called Lagrange's equations of second kind, or even Lagrange-Euler equations. I don't understand if there is any logic in the naming of this, but the math is pretty clean. So what we're going to do, we are going to look at this left-hand side of this equation, and we're just going to evaluate all the derivatives. So again, it's an exercise in differentiation. So let's start with this gradient 2 of t, okay? So what does that mean? That means that I am differentiating this by the q dot, okay? Because I said this means differentiating by the second argument of the function, okay? So what is that going to be? Well, that's simply going to be JPMJ Q dot, okay? Because this is a simple quadratic expression in Q dot, okay? So that's easy. And then I need to still differentiate that by time, okay? So I need to do this. So here it's gonna be a chain rule application. So I'll first differentiate the first one with respect to time. So I give it a little dot and copy the rest. Then this stays the same. Mass matrix is constant. We assume that it's constant, so I'm not differentiating that. So I'm moving on to the next term. And then there's the final term, which is JTMJ double dot. Okay. So that's fine. And then I need to do the first gradient of t. So differentiate t with respect to q. Okay. So again, the q only appears there because the j is a function of q. And because it's this form, it's the 1/2 of jq dot square in the mass matrix, then the first gradient is going to be this. It's going to be the gradient of jq dot, so that's what you have inside, okay? That is transposed and multiplied with mjq dot, okay? So that's a differentiation rule for squaring a vector in some norm. Okay. By the way, the 1/2 here disappeared because I had this 2 here. Now this gradient, this thing is nice because it kind of simplifies. So the gradient of jq dot, I can also, the q dot does not depend on q, okay? This gradient means with respect to q, okay? With respect to the first argument, which in this case is q. So that is simply the gradient of j times q dot, the whole thing transposed, mjq dot, okay? And now this thing we have actually seen before, the gradient jq dot. We have seen that right here, okay? Gradient jq dot. So actually remember, aha, this is nothing but j dot. Okay. So this thing actually is nothing but j dot, okay? In other words, this is precisely j dot transposed mjq dot, okay? So if I put this together, if I write the Lagrange equation, so d over dt, the gradient to t minus this, so then I am taking this and I'm subtracting that, okay? And if I look at that carefully, I'll see that this term and that term are the same, okay? So they subtract themselves, and what I'm left with is jtmjq double dot plus jtmj dot q dot, okay? So I'm left with this thing, which, as you can see, is exactly the same as here. JTMJ dot Q dot plus JTMJ Q double dot. Just wrote it in different order for some reason. So this is the same as the star. Okay? So the Lagrangian formulation leads to the same result. The one cool thing, which I won't go into details about, is that if you have conservative forces, if you can write your forces in Cartesian coordinates as the minus gradient of some potential function, where E would be a potential function, then what you can do is then you can define the Lagrangian L. The Lagrangian is simply the kinetic energy minus the potential energy. Okay, it's kind of similar to the Hamiltonian. The Hamiltonian is the sum of the kinetic energy plus the potential energy. And then you can write the equations of motion like this. Then you can write them as d over dt and minus equals 0. Okay? So the difference from what I had before is that now I have the Lagrangian here, and now there are no generalized forces. There is no funny g or anything. There is just 0 because the forces are taken care of by the Lagrangian, by the fact that Lagrangian subtracts the potential in it. Okay? And that's it. That's all I wanted to say for now. That's the basics of constrained dynamics, how you can formulate the equations of motion in the reduced coordinates. Any questions?
So how would you construct the J dot thing?
To compute the J dot thing, that's a good question. Well, yeah, you just need to, well, it's gonna be this, right? It's going to be this. So so kind of, I guess the best way to think about it is as a function, right? Like a piece of code which gets some argument. In this case, it gets an argument q and just returns what the J dot is, right? So what you're gonna have to compute the second derivatives of your x function, okay? Because the J, remember the J was already the Jacobian of x, okay? So this Jacobian of J is kind of something like the Hessian of x, okay? But again, it's a 3n by d tensor, okay? Which you immediately then contract with the q dot, okay?
Yep, makes sense.
Yes, I think that's the best way to think about it, as like a piece of code that would evaluate that. Actually, one thing I'm kind of now thinking about, if the function should have q dot as its argument. Or if it should be just a function of q.
Probably both of them, right?
I think so. I think so. Yeah, I think so. Otherwise, how you would be differentiated in time, right? Yeah, I think so. I think that's how you do it. You just pass it a q. The q will determine what the second derivatives of x are going to look like. So you need to actually be able to compute the second derivatives of your parametrization or your mapping from generalized to Cartesian coordinates. Then you pass it q dot, then you do the contraction, and then you have a function that computes J dot. I guess another way to write it would be to have just a function that computes the second derivative, just this thing, and then kind of rewrite this. You could rewrite this that isolates the another q dot. Basically, what this thing basically is, let me try to write it in a different way, this term, okay? So let me copy it first, so I'm not making a lot of confusion. And then we said that this Jt is essentially the gradient of J contracted with q dot, and then that's the funny tensor thing. There is still the other q dot, okay? So it's actually quadratic in q dot, if you think about it. That's actually the thing I got originally confused about. That there's kind of this tensor business. The J dot actually kind of simplifies it because it just reduces to a matrix. But the J dot itself is a function of q dot, and then this whole thing then becomes quadratic in q dot. So probably the best way to implement this would be to have a function that computes the Jacobian of J, aka the Hessian of X, okay, like this, like the Hessian of X, which would be the 3n by D matrix, okay? And then essentially what you're gonna do is to do a double contraction with a q dot transpose, okay? So that's X. And that of course returns 3n by 1 vector, which you can then happily multiply with m and jt. Okay, so that will probably be a good way to implement it. But I haven't done this, so we'll have to try and see.
Yeah, well, it would be interesting to see what actually happens there. I was just thinking how to avoid the tensor thing, but in general, you cannot do that, right? That makes sense.
Yeah, I mean, it's not a big deal. The tensor is basically just, so in this case, yeah, it's like a tensor. So if you are talking about a 3n by d tensor, all that means is that I have 3n d by d matrices, right? So I just need an array of matrices. 3n dimensional array, and each element of the array is a d by d matrix. And if I'm doing this double contraction thing, that means that each of the d by d matrices that gets double contracted with this q dot q dot transpose matrix. So implementing that is actually pretty simple, right? It's just a couple of force cycles.
Yeah, makes sense. Thanks.
Yeah, so implementing it as an array of matrices would be the easiest way to go. This would actually be a good exercise to actually try to implement this whole thing, actually try to simulate some of these things, like the double pendulum would be a good toy case, which has a very interesting dynamics. The rigid body is slightly more annoying because it's a little bit more complicated, but it's also possible, of course. It's kind of the standard thing in robotics, right? Because then in robotics, what you usually do, and what we are going to be doing for the skeletons, is that you have multiple rigid bodies connected together. But that's just kind of a special case of what this parametrization function is going to be. Okay, this is a general treatment that can do anything. So let's stop there for now, unless you have any other questions. This was a very good question. What is the J dot? Actually, I probably should have mentioned it in the first place. Any other questions?
So if we're implementing the rigid body in practice, like how many particles are you really going to be considering?
In practice, you will be considering infinitely many particles, because you actually, at the end of the day, you reduce it just to this 6 degrees of freedom, okay? So what you actually end up doing is integrating over the entire volume of the rigid body, and you integrate the density of the rigid body, and what you end up getting is the inertia tensor, okay? And that's essentially the analog of the mass matrix for the generalized coordinates of the rigid body. But I did not explain here you how to simulate the rigid body. Okay, this was an entirely general thing. If you want to simulate the rigid body, then you actually have to do this. Then you have to dive into the details of what this x function is actually going to be, and how the formulas will look like for the rigid body. Okay, so this is not the end of the story. This is the beginning of the story. So I didn't tell you how to simulate the rigid body yet. We will leave that for later.
Right. So one exercise, well, after trying to implement a double pendulum would be to try to generalize the formulation, to try to derive my own generalization of this formulation to an actual rigid body with an infinite number of particles.
Yes, exactly. That's a standard thing, right? It can be used in many resources, like the currently used tutorial section 4, for example. But you kind of see that the number of particles doesn't matter there anymore, right? Because it will only change some of the constants, but it will not change the equations themselves. So we actually don't have to pick any number of particles.
I guess you can say that in practice you can take whatever mesh you want as an input, and the parametrization in terms of rigid bodies could be the translation rotation, probably.
Well, the whole point is that at the end of the day, these particles are just conceptual. They are actually not there. All is there is the generalized coordinates and the Jacobian.
Yes, exactly. That's why I say you can take whatever mesh you want. It doesn't really matter how many particles.
You can look at it that way too. That's right, Peter.
But the mesh is just a surface representation. Like
no. We not. I think by mesh, Peter meant just a collection of particles, right? We don't have any connectivity here or anything like this, right? This just assumes a bunch of particles, kind of like a point-based rendering, if you want to connect it to graphics.
Yeah, that's great. It was kind of abuse of notation.
All right. Anything else? Okay, so I think I can stop the recording here. Thanks, guys.
Thank you. It was very clear and nice derivation. Thanks. It was really nice.
Thanks.